Hi there, this is part 2 of our video series for the rules of probability, addition, multiplication, complements, and Bayes' theorem. So we're going to continue with this example, which says among 144 subjects with positive test results for marijuana testing, there are 21 false positives, and among 115 negative results, there were about 4 false negatives. And so the question here is how many subjects were included in the study, how many subjects did not use marijuana, and then a probability question. What is the probability that a randomly selected subject did not use marijuana? Now, oftentimes we're going to get this types of probability problems, and it's just the text. So what is up here, what I'm highlighting. So you don't get the table. Oftentimes it is nice if we get the table, but one of my recommendations will be try to create a table on your own if it's not provided. A table just helps us organize the data and be able to pick out what is what. So here, and how do you create the table if it's not given to you? Well, I'm going to look at what the problem says. So the following results are from test for marijuana use, okay, which is provided by a certain drug testing company. So there were subjects who had positive test results and negative test results, right? So then I know that I need either rows or columns for test results, positive and negative. And then there were also people who then either were using or not using. So then that gives me my other options for rows or columns. So I chose subject uses marijuana and does not use marijuana to be my rows, and test results positive and negative to be my columns. I could have reversed this and have test results be the rows and people using and not using be the columns. It's just a matter of preference. But once I see those, I can start a table. And so I start putting things. So I know that there were 144 total with positive test results, and of those, 21 had false positives. So what does it mean to be a false positive? So that means they tested positive, so it's going to be in the positive test result, but because it's false positive, that means they did not use it. So I put the 21 there. Now for the other one, there were 159 negative results. So my total for negative results is 159. And there were four false negatives. So what does it mean to be a false negative? That means that they tested negative, but they were actually using the drug. So then I put it there. How many subjects were included in the study? So for part A, I need to figure out the total because the total is not given. So how many subjects were included in the study? Well, that's going to be the total here. So it's going to be 144 plus 159. So whatever that is. 144 plus 159 is the total, which is 303 subjects or individuals, however, whatever terminology you want to use. So because here it says subjects, I'm going to stick with subjects. So 303 people were included in the study. How many subjects did not use marijuana? So I have subject uses, subject does not use. So it's 21 plus whatever number is in here. So how do I find that value? Well, I know the total. There are 159 people who tested negative and 4 who actually do use. So I find this number by doing 159 minus 4, which is 155. So how many subjects did not use marijuana will be the total. So the total from does not use row. So that means that it's going to be 21 plus 155. And that gives me 176. And now let's fill out the rest of the table because I already have then 4, 155, that adds up to 159, 144, 21. So this must be 144 minus 21, which is, what does that give us? So go ahead and put that in your calculator and it will be 123. So 123 people were true positives, meaning they were using the drug and tested positive for it. All right, so what is the last question? What is the probability that a randomly selected subject did not use marijuana? So the probability that a randomly selected subject did not use marijuana would be, well, we already have the total of that do not use, so it's 176. So the probability of not using would be 176, right? Don't use over the total, which was this number from part A, 303. And then see if you can reduce that. And after some trial and error, trying some different things, I think 3 goes into both of those. You can reduce it to 4/7. So always try to make sure that the probability that you're given as your final answer is reduced. Let me add a part D in here that this was not in the notes, but let me just add it. What about the probability of using the drug? How would you find that? So the probability of using would be, you look at subjects who are using marijuana, so it will be the total here. So 123 plus 4. So what is that? 123 plus 4 is 127. So it will be 127 out of the same total, 303. And so let's reduce that if we can. But in this case, we can't because 127 is a prime number. So the only factors of 127 or of any prime number are 1 in itself. So it doesn't reduce unless 127 goes into 303, which it doesn't. So then that's as far as you can go with reducing this fraction. But the reason that I wanted to add this problem is because notice that then the probability of not using and the probability of using. So a person in the study is doing one or the other. So the probability of using or not using will always be 1, right? If you pick a person, a subject from the study, they're either using or not using. So this is going to be true. And which brings us to complements. So these are complements of one another, right? The probability of using marijuana is this. The probability, then the complement will be a person is not using. So these probabilities should add up to 1, which notice that they do. If I take the probability of using 127 out of 303 plus the probability of not using, so my probability of not using is here. I'm going to take the unsimplified one because then I will have a common denominator. 176 out of 303. That gives me 303 out of 303, which is 1. So that leads us into complements. So a complement is the event that when event A does not occur. So here, right, if I say my event A is using marijuana, then the complement of A is not using marijuana. And so one of those has to occur. So back to our example of using and not using, right? If I pick a subject, they're either using or they're not using. So that probability together is going to be 1. So that's what this says. We are certain that P of A or P of not A will occur. So this means that the probability of A plus the probability of, whoops, that should say not A equals 1. So I changed that. So for this example, a 6-sided die is rolled. Event A, the number roll is at least a 5. So my sample space is 5 or 6. So what does at least 5 mean? So at least 5 means 5 or more. Right? So then what is the complement of at least 5? So if at least 5 means 5 or more, then not at least 5 would be less than 5. So the complement of A will be less than 5. And so what does that mean? So that means that the complement of A, so not A, is 1, 2, 3, and 4, right? At least 5 means 5 or more. Then not A, not at least 5 means anything less than 5. So 1, 2, 3, and 4. So that's how we find the complements. So let me add another example here. Going back to our deck of cards example. So in a deck of 52 cards, event A is getting an ace. So what would the complement of A be? So not A. So this will be, so if A is getting an ace, then not A is getting anything other than an ace. Getting a card other than an ace. So in terms of probability, what does that tell us? So what if I say find the probability of getting an ace? So the probability of getting an ace, so back to the deck of 52 cards, there are 4 aces, right? So it's going to be 4 out of 52. And we can reduce that to 1 over 13. So what about the probability of not A? So the probability of not getting an ace. What will that be? Well, if there are 4 aces, then the rest of the cards are not aces, so there are 48 out of 52. And again, we can reduce that to, well, I already know this, divided by 4 is 13, which is prime. So what's 48 divided by 4? 12. So 12 out of 13 will be our probability. Now notice that ace and not ace, those add up to 1. So the probability of ace or not ace is the probability of ace plus the probability of not ace, which is, what did we say, 1 over 13 plus 12 out of 13. So notice that that adds up to 13 out of 13, which is 1. So another way then that I can find the probability of not ace, another thing that I could have done then is say this is 1 minus the probability of ace. Since they add up to 1 together, right, probability of ace plus probability of not ace adds up to 1, I can say 1 minus my known probability. So 1 minus 1 out of 13, which will still give me the 12 out of 13. So that's another kind of like a shortcut of finding the probability of the complement, not A. So let me write those down. So here are rules of complementary events. So as we discussed, the probability of A plus the probability of not A is equal to 1. So the A bar means not A, the complement of A. So then the probability of not A is 1 minus the probability of A, and likewise the probability of A is 1 minus the probability of not A. So essentially solve for one of these, right? From the original, you can think of it as an equation. So if I want to solve for probability of not A, subtract P of A from both sides, right? So if I have PA plus P not A equals 1, subtract PA from both sides, and you'll get the second line. The probability of not A is 1 minus the probability of A. And this is helpful because if I know the probability of A, and I don't have to go back to the sample space to find the probability of not A, I can just say, well, since I already know the probability of A, the probability of not A is 1 minus my known probability, instead of having to go back to the entire sample space, right? Like here, when we did the ace, we said, okay, the probability of ace is 4 out of 52. So instead of thinking, okay, how many not aces are there, and trying to think, oh, there are 48 other cards that are not aces, I can just say, well, I already know the probability of ace is 4 out of 52. So the probability of not ace is then 1 minus 4 out of 52. And so that's gives me a shortcut of finding the probability of the complement by not having to go back to the sample space. So let's try this example. You survey a sample of 1,000 US voters and record the age. The results are provided in the table below. So the question is, for part A, what is the probability that the voter will be between 25 and 34 years old? So I know there's a total of 1,000 and I'm getting the frequency distribution table for it. So I can just find the 25 to 34-year-olds. So that's this entry. So I know then there are 366 voters in that age range. So the probability of being 25 to 34 years old is 366 out of 1,000. And so let's make sure we reduce that, which I think only dividing by 2 works. So this will be 500, and then when you do 366 divided by 2, you get 183. So that will be my probability. Okay, so part B, what is the probability, as I'm reading here, what is the probability that the voter will not be between 25 and 34 years old? So if my event A is being 25 to 34 years old, then I'm finding the probability of not A, so not being that. So I can try to add up all these, right? 54 plus 233 plus 180 plus 125 plus 42 and get it. Or I can say, well, I already know the probability of being 25 to 34 is this. So the probability of not being that age is 1 minus 183 out of 500. And so I can just do this probability. So get a common denominator, right? So 500 over 500 minus 183 out of 500 and get what that is. So what's 500 minus 183? So I got 317 out of 500, and I believe that that is already reduced. So this gives me another way of finding the probability of the complement, right? And notice that if you did do, right, add up 54, 233, 180, 125, and then 42. So if you did it that way, so not 25 to 34, add all those up and then divide by 1,000. So when you add all those up, you will get 634. And then you have to reduce that. So once you reduce it, you get 317 over 500. So it kind of depends what kind of work do you want to do. Right here, we have to get a common denominator. Here, you have to add up all the other values, all the other frequencies. So if I had more things, it's just more work. So it just kind of depends. What work would you rather do? Get a common denominator or add up all the other values? So I personally, I would rather get the common denominator, because if this was more, right, if this had like 10 rows, then that's just a lot more work than getting a common denominator. Okay, so that is the rule of complement. So we'll move on to multiplication. So I'll record a different video for the multiplication and talking about independent events and Bayes' theorem.